Yeah, started recording.
Okay, yeah. So as I was saying, this will be a lightweight set of slides, mostly my own personal views. You may agree or disagree. So as we have discussed, and some of you have actually raised some themes that we can discuss about the future of computer architecture, keeping performance and security in mind. So here I'm talking about a time zone which is kind of 30 years from now, or let's say 2050. So the first thing that comes to my mind is quantum computer. So if you are not aware of what exactly it is or what exactly it can provide, so this is a 100,000 feet view. It's not a detailed technical set of slides, but just to give you what can it be, like what can you achieve through this. Okay, so there are these myths that I see usually online that quantum computer is the fastest computer. It's like you know you can equivalent, or you can create an equation that quantum computer is hundreds of thousands of supercomputers. Similarly, hundreds and thousands of data centers. The answers to all these equations are actually in all these equations are actually not correct. By definition, they are not correct. Okay, so then how will you compare? Well, you should not compare because it's a different computer, or the paradigm is completely different. It's not the same old paradigm that we are, or the current paradigm that we are currently using. Okay. So next time if someone says that, okay, it's faster than ABC, they just pause for a minute and say that, okay, that's not the right metric to compare. Okay. So what is it exactly? So this is how you can, I hope slides and the picture is visible. So this is from Google. This actually, still at a baby stage. If I have to compare it with, all the other fields of computer science research, plenty of things to be done. Most of the things are actually at the infant stage, but it's still there. Actually, people have already designed. Maybe it's not the quantum computer per se, but they are kind of improving day by day, month by month, year by year. Okay. So what's the difference when someone says quantum computing or quantum computer or this quantum computing paradigm? Okay, I'm using the word paradigm because if you want to run something on a so-called quantum computer, you need quantum algorithms. Okay, so that's a different set of algorithms. So it's an entire, the CS stack that we have been studying: problems, algorithms, then the logic gate, the notion of binary bits, and all. Everything has to change. And one of the most prominent thing that is different is the moment you jump to quantum computing paradigm, instead of operating on a bit, which eventually gives you either 0 or 1, with quantum bits, it actually gives you a huge search space in between 0 and 1. So just to give you top level analogy. So if you are thinking about the binary system, it's like a north pole and south pole. Okay, if you want to define the quantum computing paradigm, keeping north pole and south pole in mind, then these are all the possible states that are possible between the north and south pole. So that is what the quantum computing paradigm is. So it has its own properties. Two of its properties are like superposition and entanglement. And I'm just showing you one example of superposition where, at a given point of time in a binary system, you'll have either 0 or 1. You can't have a, in between value. But here you can have a state that says, okay, at this moment, I have, probabilistically it's a 20% 0 and 80% 1, just to give you an analogy, right? And you can think about the number of possible combinations that you can get because of superposition, right? You are actually superimposing, you are actually, kind of creating, I would say billions, if not less than that, in terms of the combinations that are possible just by looking the values between 0 and 1. Okay, so theoretically it's a pretty powerful paradigm, because now you think about the computations that you can do, let's say in one cycle, right? Currently we are dealing with 2 to the power n, where n is, let's say n-bit processor or n-bit computer or whatever. Now here, this value will be super, super huge because of this superposition, right? What's the utility? Like, why will someone go for this quantum computer or this kind of paradigm? Well, think about questions like finding the factors of a 4,000-bit number. 4,000-bit number. Okay, so currently we are using, let's say, 32-bit, 64-bit. Let's say the query is find all the factors of a 4,000-bit number. So if you can just pause for a bit and then try to correlate whatever you have learned from your mathematics course, you will finally realize that no matter how many supercomputers you have in the entire world, and no matter how much energy you have in the entire planet, uh, to just find out all the factors of a 4,000 or 6,000 or 10,000 bit number, it will just take thousands of years or maybe more than that. Okay, but the high level utility is if you are going for a quantum paradigm, it can be done in few hours. Okay, so that's the impact that we are talking about. Um, if factorization is not a big deal for you, then think about problems like how organisms behave, right? Think about all the interactions. How will you model them? And even if you want to model everything through a supercomputer, it will take years, right? But having said that, there's a disclaimer. Definitely, the quantum computers are not for speeding of matrix multiplication or the accelerators or the tensors that we are discussing during our course, right? So it has its own utility. So that's why I said you should not compare the notion of quantum paradigm with the modern computing paradigm. They are like two different things. Okay, so if you compare, it will be like comparing an apple with the orange. Okay, they have their own utility and they have their own issues. Okay, any questions here before I move on to some other topic? Or it's boring? At least say yes or no.
No.
No questions. Okay. So let's look at some other things that may happen. Okay. So let's look into the possibilities that may come up in the next 20, 30 years, right?
Sir,
Yeah, go on.
excuse me. Sir, so how do we like realize those qubits like in between values? Here, like
No,
on and
go
off,
on.
like in bits.
Yeah,
Uh-huh.
it is not. So you have to change the way you think. Starting from your physics.
Okay.
Okay, so whatever we have learned in our curriculum, starting from your plus two physics till now, you have to unlearn everything to learn how quantum computing works. Right? Because that's why I'm saying it's a completely different paradigm, even from the basics, right? Forget about the architecture part of it or the processing capability part of it. The theory itself, right, that drives this paradigm, that is completely different.
Okay.
So it has to start from physics, to be honest.
So
Then
the
then
memory structure and everything will be different. Like
sorry.
memory structure, like that will also be different, right?
It's not about memory. So memory is just I would say it's a container to store data, right?
Yeah. Yeah.
But the more important is how are you accessing this data and what does it mean? So now if I want to access a particular address, I'm sending a 32-bit address, and that gives me the content of that, right?
Mm.
But here I'm giving you uncertainty, right? So at a given point of time, I'm not sure whether it is completely zero or completely one. It can be something in between.
Right.
So you need a completely different mindset to think about the algorithms. Let's a simple example. Let's say sorting algorithms, right?
Mm.
What do they do? They compare whether two neighboring numbers are less than, equal to, or greater than, right?
Mm-hmm.
So now let's say I compare values like 10 and 11. So you can actually directly you can put a binary partition that okay 10 is actually less than 11, right? If you look at the binary representation, right?
Yeah.
But now if I bring the notion of uncertainty, you will say okay it's like 0.7% or like 70% it's kind of 11, 30% it's kind of 10. How will you sort?
Oh, that's
Right? I'm just kind of giving you at a pretty high level. Okay, I'm not giving you the technicalities, but think about all the complexity that will come from the very basics of our education, right? The computer science education. Forget about architecture,
right.
right? So yeah,
Thank you.
okay. So I was talking about what can change or what may change in the next 30 years. So if you understand the notion of ISA and microarchitecture, right? ISA like x86, ARM ISA, RISC-V ISA, they just tell you, okay, these are the instructions, these are privileged instructions, and these are the possible things that you can do with these instructions, right? Microarchitecture is whatever we have discussed in this course, like caches, TLVs, prefetchers, whatever, right? Whatever that is there on chip to improve performance. Now, just to make sure that we have better security, better flexibility, let's say as a programmer, you can go for a completely different way of defining IS and microarchitecture. For example, simple question like cache memory, right? Or the notion of caching. Why not caching can be a part of ISA, right? So now the moment you use x86 ISA, you can say that, okay, address number A to G, programmer can use it as, let's say some rules, some semantics, right? That will give you more control, right? As a programmer or at a, high level in the system stack, you can actually do optimizations which are pretty application specific. No need to go for monolithic generic cache hierarchy and then try to optimize, right? Think about cache attacks. Now, if you are saying that things are kind of open, it's just kind defined in the ISA itself, then it can give you more control in terms of who can see, who can't see, right? We will talk about that maybe in few slides later. The second thing that will happen that has already started happening is we have looked at few papers in this course. Instead of a horizontal approach where we try to get more and more performance, you will see architecture is actually becoming a vertically integrated research area, right? Where you actually build application specific or domain specific architectures, but at the same time you actually design them by talking to folks who are working on compilers, runtime, and other things, right? So again, this boils down to the previous slide where I talked about the notion of ISA. So maybe the contract will be revisited. Maybe the architecture's books will be rewritten, right? Saying that okay, now the notion of microarchitecture can come even during compile time, right? Who knows? I'm just thinking out loud, right? We have already looked at notions of like processing in memory, processing near memory. So that are nothing but data centric approach, right? So it's actually a different approach from the conventional one-by-one model, right? And slowly, if you kind of go up in the system stack layer, you're actually talking about a completely different system stack where everything is designed, keeping all other layers in the system stack. They're not designed in isolation the way it was designed in the past or maybe currently, right? Then the moment you talk about architecture for performance, first thing that comes is applications, right? What are your killer applications for which you want to improve performance? So you guys are using some benchmarks for your project. If you look at the application domain, ML, obviously everyone knows about it. IoT is a big thing. Yeah. So Internet of Things and the kind of operations that we do on IoT devices. And by the way, all these IoT devices are connected to some servers, right? So no matter what kind of IoT device you use, they are actually connected to some server, right? And there is an estimation that by 2025, which is just few years from now, you will have billions of devices. So that means that will put extra load on all these servers because they will keep on getting data, and you have to process at a pretty faster rate, right? It may happen that you have to, data mine it, you have to inference something, even at the IoT itself, right? So that's the notion of this edge computing and all. So what will be the role of architecture? How will you design computing engines that can make the life of IoT device, pretty easy or simple, right? This is something which is pretty personal. No one talks about secure programming. If you look at all the attacks that we talk about in this course, those attacks won't be possible if the programmers, when they wrote those programs, they are aware of the microarchitecture, right? So simple attacks like Spectre, right? No one talks about the notion of speculative execution, wrong path, or whatever. And that's why when you code, obviously you don't think about all these microarchitectural flaws or designs, right? You just code just for the sake of coding, right? So maybe, right? Maybe there is a need for courses on secure programming, right? Where yeah, you teach the entire system stack, and you also teach or train students, giving them programming assignments, but telling them that okay, write it in such a way that no matter how clever the attacker is or spy is, data won't be leaked, right? So this will be kind of a dream course for me. I'll offer it pretty soon if I get some TAs, good TAs who can actually help me in this. Otherwise, it will be offered after 2050. Uh,
Hello, sir.
Second, yeah, go on.
Uh, can you give any like simple example of like how secure programming will look like, or what things might be considered in secure programming? Any example or that
Simple
sort?
example, right? If you look at the notion of the very first lecture that we had in January, the main or the crux behind all these attacks where there is some control flow, data flow, right?
Yeah.
If this condition holds true, then this AES library will do this, otherwise it will do something else, right? So at a high level, the first mantra will be don't have all this control flow dependency, right? So you make sure that all your secure data and code, they go through, or if you look at from the code flow point of view, there should not be an if condition when you are accessing something, right? It should be like in one go, right? And so if that's the case, that is actually making the job of an attacker difficult. Because now, if you're talking about, let's say, some crypto library, and if there are no if else statement, or if there are no controlled dependency, then whenever you run, let's say, for that AES library, you will see the same set of addresses all the time, right? You won't be able to differentiate, okay, when you access a particular address A and when you access another address B, right? This is just a simple example. Does that make sense?
Yeah, but the like inherently the ASC or any program you take or any like algorithm you take, there will be control flow divergence, right? There will be if else
There
statements.
will be, but you can convert that control flow into a sequence of non-control flow statements,
Okay.
right? So
Uh,
that's what I'm saying actually. So let's say if you say that that's actually happened. If you look at the latest AES, because of cache attacks, they changed their code, and that's what I'm talking about, secure programming.
oh, okay.
Uh, yeah, so if you look at the old version of crypto libraries, you will find that, okay, if this condition holds true, then this particular bit will be 1, otherwise it's 0, right? Now, irrespective of if condition becoming true or false, you do the same set of accesses all the time. Here, the goal is the security. I'm not concerned about, any other aspects of, let's say, performance or anything else,
Okay. Okay.
right? Yeah, this is a pretty high level example, right?
Yes, sir. Okay, got it.
Okay, yeah. Next thing that we discuss pretty, I would say few lectures and then few papers, energy efficiency, right? And we actually discussed that in the modern era, communication is actually the bottleneck or the problem to solve and not the computation, right? And then especially in the context of domain specific accelerators or architecture, you will find that, okay, getting the data actually from one source to another destination is actually the bottleneck. And how can you write programs such a way that you reduce the communication cost? So think about the algorithms course that you must have taken, the CLRS book, right? Every time it's just the time complexity. No one talks about communication complexity, right? But that will come eventually, right? You have to start evaluating an algorithm based on the communication cost on a real system, right? So again, this has already started, and it will be, it will at least it will stick for, if not for next 30 years, at least for next few years or a decade or so. Finally, CO2 emission. Okay, I think all of you are aware of it. And but how does it correlate to architecture or a course on performance and security from architecture, right? Just think about all the streaming services that you use, Netflix, Hotstar, Amazon, whatever, right? And the number of mobile phones that you use, and the number of queries that go into data centers, right? That will give you the answer. Now, then what's the solution from the architecture point of view, right? What can you do? So you have to come up with microarchitectural techniques which are sustainable, right? This needs a different way of thinking, but energy is actually a proxy to start with. If you want to come up with, let's say, sustainable architecture, then first you have to make it energy efficient, and then you can go for the carbon emission. Okay. So maybe we will have metrics in the future, maybe after 10 years, that says that, okay, 3-level cache hierarchy, CO2 emission, some XYG, right? Again, I'm just thinking out loud. But if you look at all these articles, right? So this means this is actually the thing that is happening, and industry is actually serious, right? The numbers are like 2030, 2040. So we are discussing about 2050. So definitely this will be one of the primary theme in the system design or in the architecture design, right? So like Apple is talking about carbon neutral iPhone. So watch out. Then let's look at the security side, right? How can you redesign microarchitecture? Well, at least personally, my approach will be redesign the entire stack, right? And then that again boils down to the same old mantra that, or the future that I was envisioning, is that you need to redefine the role of ISA, microarchitecture, operating system, compiler, whatever, all, right? And then come up with semantics that tells you from day one when you start designing a system that who can do what, right? So this is a simple protocol that I have put at the bottom, that if you can't see something or touch something, then no matter what, the system should not give you any information about the addresses or the resources that you can't see or touch, right? Pretty simple protocol, but you have to convert the simple protocol into implementation in the entire system stack, right? But definitely it's not a one layer mitigation approach where you say, okay, I will redesign microarchitecture to provide security. So it's like, you are fixing one layer of the entire stack, but security is actually a problem for the entire system stack, right? If something is not secure, it will come out in some form or other. It will come out. Again, this slide is highly biased and highly personal, but it's my opinion. We talked about all the possibilities that can happen. The other possibility that can happen is, if you have looked at or if you have observed last 10 years, most of the big companies, they are actually pushing for automated stuff, right? Nowadays, it's just a matter of pressing an enter or installing an app, right? So it's actually good for the end users, right? So that makes the life of billions of people around the world easy. But it's actually bad for CS students. Like when I say CS, CSW, or any anyone who will design a system or build a system, right? And the question is why, right? So the more automated stuff you start using, you will stop, appreciating the abstractions and the other things that you have learned or you are learning now, right? And suddenly it will be kind of free lunch, right? Maybe by 2050, this is again my speculation. People like me or anyone who is taking this course, they will become a critical mass of a dinosaur, right? Because hardly anyone will understand, oh, okay, x86 has these instructions because of which this particular application works fast, right? Maybe very few folks will be there who will understand these instructions, forget about writing code or optimizing them, right? So that is the other side, or the worrying side of the technology revolution, right? Things are becoming more and more automated. You have to just use it blindly like a black box, right? And the moment someone gives you black box, you stop reasoning about it, and that's where the problem starts. This will be me in 2050, right? Hopefully I won't become a dinosaur, but only time will tell, right? So this I will stop, and we can discuss more about this themes that I just discussed at a high level. So you can open up, and then you can talk about anything that you feel like, or you can comment on this. It's perfectly fine if you disagree with all this that I am talking about. No issue. We don't know what will happen. It's just a speculation. So Birendra, you may stop the recording.